Section 10.3 is going to talk about a special type of angles, and this is actually, there are two sections we're going to talk about special type of angles involving circles, okay? This is just one type today, and then the next section we're going to see a lot of different types, okay? So the one we're talking about is called an inscribed angle. Now, so far we've talked about one type of angle involving a circle. What was that called?
The central angle.
Central angle. Inscribed angle is a little different, okay? An inscribed angle is an angle whose vertex is on the circle. Okay, so first of all, that has to be true. So if you look at this circle here and this angle, notice the vertex is directly on the circle. Now, some other criteria. It says whose sides contain chords. So the sides have to be chords of a circle. Now, contain chords. If you extend this out as the ray here, obviously this goes past the circle, but notice the sides PA and PB, those segments are actually chords.
All right.
Okay, so that's why this is inscribed angle. All right, so this in this picture, angle APB. Now you could technically say this angle P because it's the only angle in the picture. Okay?
Right.
Now, we've seen this word before, but just a reminder, an intercepted arc is the arc that lies in the interior of an inscribed angle and has endpoints on the angle. Okay, so the arc, and it lies inside the inscribed angle. All right.
So we're talking about like arc AB in this picture.
But the endpoints have to be on the angle. So if I had some other points right here, let's say this is D and C, that wouldn't be an inscribed arc or intercepted arc because the endpoints are not on the inscribed angle. Okay. So the intercepted arc in this case would be arc AB. The key is an intercepted arc endpoints have to be on the angle that it's kind of intercepted.
The entire arc that's inside that circle. Or inside that inscribed angle.
Okay. Now, there's something cool about inscribed angles in relationship to that intercepted arc. So that's why we need to know that vocab.
All right, so we have several theorems that we're going to be looking at today. The first theorem is talking about the measure of an inscribed angle. And it says that if an angle is inscribed in a circle, so again, we have an angle that's inscribed within a circle. So you see like angle ADB is inscribed in that circle. Then its measure is half the measure of its intercepted arc.
Okay.
Okay, so whatever this measure is,
and measure is degrees.
so I'm going to say if it's x degrees, then this angle right here would be
A half of that.
half of that in terms of degrees. Okay? Now, we've talked about another relationship, and you'll notice that on my picture right here, I've got another angle. What angle is angle ACB?
That's the central angle.
Right. And this central angle also has the measure of what?
The intercepted arc, so that means that is also, if you labeled it, x degrees.
X degrees. So we have, just to talk about some relationships that we know, we can talk about the relationship between a central angle and its intercepted arc. And now we know the relationship between an inscribed angle and its intercepted arc.
Which means we could compare the inscribed angle with the central angle because of that relationship. They both have something in common with the arc measure.
Right.
So depending on, is it half, is it just exactly? Something to keep in mind, guys, and you're going to hear us say this more in section 4, is a lot of it's about where that vertex is located.
Absolutely.
So if the vertex is located on the circle, notice it is half of that intercepted arc. All right, and that's because notice how that angle is kind of forced to be further away, so it's making that degrees a lot smaller.
Yeah. All right.
All right, here's another theorem. It says, if two inscribed angles of a circle intercept the same arc. All right, so if two of them, they're both inscribed angles, right? And again, what makes them inscribed is that they have a vertex that's on the circle and made up of chords, basically. Right. And they intercept the same arc. Now, if they intercept the same arc, then those angles will end up being congruent, right? Because if they're intercepting the same measure, essentially,
then it's the half of the exact same measure.
Exactly. So in this picture, which angles would end up being congruent?
So angle ACB.
And I'm just going to call it angle C.
Okay. And angle D, because they're both inscribed within that circle, and the arc that they're intercepting is arc AB. So
And
they're both half of that arc AB
And I love
measure.
that because notice there's no theorem name for this. So if you had to explain, I love how you said that. The reason why is they're both, first, inscribed angles. You have to know that they're inscribed because this involves that intercepting the same arc. And that's why they're going to be congruent. All right? What other angles do you see?
Now, and those are the ones that I've got like as a blue and a purple. But as I look, angle A would also be congruent to angle B because they're both inscribed angles that are intercepting arc CD.
Yep. So these are going to be congruent as well. Good. So that kind of helps because if you know one, you know the other. It makes it pretty easy to figure that out.
Absolutely.
Good deal.
Okay, next theorem. We've got several of them today. This one looks a little wordier, but don't let it throw you. It's not any harder. It is wordier. So it says if we have a right triangle that is inscribed in a circle. And inscribed is, just keep in mind, it's inside the circle, but its vertices are touching the circle. That's what we're talking about. Any figure can be inscribed.
Well, and really, that means all of its angles are inscribed angles, like you're saying there. Yep.
So this angle A is going to be half of the measure of arc BC. And angle B is half of the measure of arc AC. Looks like it's probably a semicircle, though, so we're going to get there. And then angle C is half the measure of arc AB.
Good. And that's using the theorem that we just learned.
Right. In fact, that kind of ties into what this is. It says, then the hypotenuse is the diameter of the circle. Now, let's talk about this for a second. Okay, we said that angle B, if we know that it's half of the measure of this arc right here, what do you notice about this arc?
Well, it says if it's a right triangle first.
Yes.
Okay, so you would have to know which angle is a right angle, so I'm assuming that's the right angle.
Right.
And you have the inscribed, then that arc AC is just twice the size of that angle B because that's the intercepted arc. So that would be 180 degrees, which then that makes that a semicircle, which would force a segment AC to be a diameter.
Exactly.
Oh, that makes sense.
It does make sense, and it's something you don't necessarily need this theorem. It can easily be proven. But if you notice that happens, you automatically know that that is the diameter of the circle. Okay? Now, conversely, if one side of the inscribed triangle is the diameter, then it's got to be a right triangle because, again, if we know this is the diameter, we know this is going to be 180 degrees. And therefore, when you look at that inscribed angle, you know that that's half of that 180, so this is going to be a 90 degrees.
Which forces that to be a right triangle.
Yes.
So this one thing I'm noticing, it's wordy, but it's actually, in a sense, you could put it together and make a biconditional. They just didn't do that this time.
Right.
So it's like a 2-in-1 in a sense.
Exactly. And again, if you notice you've got your diameter, obviously it's that angle that's across from that diameter that is going to be your right angle. Another thing to kind of be aware of, if this is the diameter of a circle, and I know that these are just two other chords, could either of those chords be larger than the diameter?
No.
They can't be, right? So that has to be the hypotenuse every time because that diameter is the longest chord within a triangle or within a circle too.
Okay, I think this is the last theorem that we're going to learn today, and then we have several examples to kind of apply. This is a biconditional statement, so they kind of shorten it for us. So this one can be interpreted forward and backwards, so keep that in mind. It says, a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. All right, so first of all, if you're kind of interpreting it forwards, that would mean if a quadrilateral is inscribed in a circle.
Okay, so we do have a four-sided figure.
So if I gave you that the quadrilateral EFGD is inscribed.
So all of its vertices are touching the circle. They're all forming inscribed angles.
Exactly. Then we would be able to conclude what?
That angle E and angle G are supplementary.
And notice which one she's choosing, guys. It's the opposite angles. I think this is one that we kind of get mixed up with. We'll talk about why that is. Are supplementary and
D and F are supplementary.
Now, basically that would be the forwards. All right. If you go kind of backwards, it would be saying you'd start with the supplementary angles, then you can conclude kind of the inscribed. Okay. So basically, if I give you these angles are supplementary, I'm going to write these kind of quickly. And then we can say it's inscribed.
Yeah. Now, let's start thinking about the why while Mrs. Palermo's writing that down. If you take a look at angle E and angle G, notice that when you think about their intercepted arcs, those two arcs that they're intercepting, so angle E is intercepting the circle, and we're going to have arc DGF. Okay? And then where angle G is intercepting is going to be leaving us with arc DEF. Those two arcs together form the whole circle. We know that the inscribed angles are only half of the measure of the intercepted arc. But when I'm taking half of two things, half of the sum of two things that add up to be 360 degrees, then it's going to leave us with just the 180 degrees.
Exactly. That's a great, I love how you explained that. That's a great explanation. Now, here's the thing, though, keep in mind, it's the opposite angles. We often, when we dealt with quadrilaterals back in chapter 6, back in like December, we were talking about special types of quadrilaterals, and parallelograms, for example, was a very common one. And opposite angles weren't supplementary.
They were often congruent.
They were the ones that were consecutive. So just be careful. Consecutive angles don't have to be supplementary. Now, if they were, that would mean that it was a special type of quadrilateral. Can you think of a quadrilateral that would be inscribed no matter what?
Like a square.
Square or
a rectangle.
Because both of those have opposite angles that are supplementary.
Right.
But any other quadrilateral out there could be, as long as the opposite angles are supplementary.
So with that logic, then that means that I could never inscribe a parallelogram, just a regular, like a something that's not more specific.
Not a square or a rhombus, basically.
That in a or in a circle.
Exactly. So again, the opposite angles are supplementary when you're talking about inscribed quadrilaterals. Just those kind of go together. All right. So just kind of keep that in mind. All right. Let's put this to use. Some of these theorems and definitions and all that.
That's right. And I'll tell you that some of these examples are going to be super quick and easy. So some of them try on your own.
Yes.
And then if you get stuck, come back and check them. But definitely try some on your own for all of these before you watch this part. Okay, so we are trying to find the measure of arc AC.
So I'm trying to find the degree amount. And here's my thought, is I look in what I'm given. And I'm given that angle B is 70 degrees. Now, that to me is an inscribed angle because its vertex is on the circle and is made up of chords. So I know the relationship between an inscribed angle and its arc is that it's half of the arc. Okay? So that angle B is basically...
So half of this measure of this arc
will get you the angle B measure. All right? So if I want just arc AC, I'm just going to double that.
Right.
So arc AC is 140 degrees. The intercepted arc should be larger than in the inscribed angle. Keep that in mind.
Awesome.
All right. Try these on your own. So find the measure of the arc and the angle. Okay, so let's just do the arc first.
All right. So looking at what we're given, we're given a central angle.
Okay, let me make a little note. This is the central angle.
Which that tells us, we know that the central angle is exactly the same as its intercepted arc.
Okay, so that means that...
arc QS is going to be 130 also.
Cool. All right. Now, what's the angle we're finding next? What kind of angle that is?
We're finding the angle that's the inscribed angle.
Now, the thing is, it's all about the arc that intercepts. Keep that in mind. It's angles and arcs kind of go together. So what's the relationship between this angle and its intercepted arc?
It should be half of the measure of its intercepted arc.
And the intercepted arc is 130. So you just do basically half of it, or divide by 2, and you get
65.
Okay.
All right. The next one says, find the measure of the arc or the angle. Okay. So this one, notice that what we're finding is 3 angles. All right. So if you take a look here, what is the measure of 90 representing?
That's the measure of arc AE.
AE. And we know that because that's what it's right in the middle of. Now, look at all the angles that they're asking about. Angle ABE, angle ACE, and angle ADE.
Well, I'm going to start with angle ABE. I notice that that's an inscribed angle again. And I know that an inscribed angle is half of its intercepted arc. And so since that's 90, we're going to do half of that gets you 45. Now, that's that angle ABE. Now, I'm looking at the next angles that we are asked to find. They all intercept the same arc. And we learned a theorem that if inscribed angles intercept the same arc, then they're congruent. So that means angle ACE is 45.
Because I could do another half of 90 and another half of 90, but
it's going to be the same thing. So 45 degrees as well as 45 degrees.
Awesome.
So hopefully you can do this one on your own too, guys. So what's the measure of angle C? Now, what are they giving you information about?
They give us angle B.
Okay, I'm going to label that.
But that's 44.
And what kind of angle is angle B?
It's an inscribed angle.
Okay,
now.
now.
And I can see that its intercepted arc is arc AD.
Okay, now what kind of angle is angle C?
It's also inscribed, and it's intercepting the exact same arc.
So if they're inscribed angles intercepting the same arc, that means
they have the same measure.
So that means this is
44.
44 as
now,
well.
Again, if you forget the theorem, keep in mind you could have doubled it really to find the intercepted arc and gotten 88 and then done half of that to get to C. It's just silly if you know the theorem.
But again, notice that explanation. What Ms. Hugravy said. They both inscribed angles with the same intercepted arc.
And that's important. If they're not inscribed, it won't work. It's got to be inscribed.
So just kind of keep that in mind, because sometimes we ask you to explain, so this would be a good explanation.
All right, for this next one, they tell us to find x. And I want you to look at what we have in this picture.
Well, I'm looking and I'm seeing that the triangle is inscribed, because all the vertices are on the circle. So all of the angles that make that triangle are considered inscribed angles.
Wonderful. They want us to find x, but notice that there are no measures on here at all.
Okay, so what I'm thinking is I noticed that one of the sides of that inscribed angle is actually a diameter, that segment AB. And we learned a theorem, which you didn't have to know it, but we learned one that said if the diameter of an inscribed angle or of an inscribed triangle is one of the sides, then the angle opposite it is a 90-degree angle, a right angle.
Right.
So that means that 3x is equal to 90.
Right. And again, if you forget the theorem, that's okay, but the fact that this is the diameter is important because that means this is a 180-degree arc.
Which would half of 180 get you 90. That's why 3x is 90. So x ends up being 30.
Love it. Oh, sorry, it's not degrees. It's just x. So x is 30.
All right. One more example.
All right.
It says find each angle measure. Now, what are you seeing here?
I'm seeing that we have a quadrilateral that is inscribed in our circle because all of those vertices of that quadrilateral are on the circle.
Okay, so we're thinking inscribed quadrilateral, which means what?
That opposite angles are supplementary.
All right, let me write this down. So the inscribed quadrilateral essentially means the opposite angles are supplementary. So, which angles would be supplementary in this picture?
So, like angle A and C.
These two angles here would be supplementary, which essentially means what are we going to do with those measures?
Well, we can write an equation. So, let's say 40x plus 10y is equal to 180.
So, here's the deal, guys. This is just applying the theorem.
Right.
Okay, using the new material to kind of write an equation. All right. We have done so far kind of the geometry concept behind it. Now, here's an issue with this equation.
Yeah.
There's an x and a y. We cannot solve and find the value of x and y, which here's the deal, guys. That's what we're going to need to do.
Right.
We got to find x and y to find these angle measures. I don't know either one, so I can't really just use this equation.
I need another equation.
We need another equation. If there's two
sounds
unknowns,
like a system.
If there's two unknowns, we need two equations. So there's one equation.
Okay. Well, B and D are also going to be
exactly. So
supplementary.
These two, we still need to use that idea. The opposite angles. There's another pair. So we can add those. Here's my second equation.
Is going to be 22x plus 19y is equal to 180.
All right, so here's the deal. This is, now we're solving a system. This is all back to Algebra 1. Okay, so this is, you've done the geometry, now we got to remember last year. Okay, it's been a while. We've done some of these here and there. Now, refresh my memory of some good options in solving a system.
Okay, we could do substitution, which means that I would want to get one of the variables by themselves.
Okay.
And then put that equation that I'm left with into the other equation and solve.
What's the other option?
The other one is elimination, which elimination is when I've got them both in standard form, which we do here. We would need to get opposites for one of our variables.
Okay. So here's the deal. In the end, it really doesn't matter what you do. It's what you're comfortable with.
Right.
My preference on one system might be different on another, depending on, again, what's given to you. Okay.
Right.
And everybody's going to be different. All right. So what do you want to do?
You know what? I'll tell you, this is one of those that it wouldn't be that hard to get opposites for one of our variables.
Okay. Which variable?
Let's do opposite. Gosh, does it? We're going to have to do work either way. Let's do opposite y's.
Okay. So
Let's
she's
just
looking to see, let's make sure these are opposites. And the reason why is because we want them to be eliminated. We only can really truly solve an equation with one variable in it. So we need to get rid of one of the variables. So we need to make these coefficients to be opposite numbers, like 5 and -5 are opposite.
Right.
Right? So we need to find a number, okay, that we're going to multiply either one or both of them. So that way these are opposite coefficients.
Sure. And I have a feeling most people would just say, let's multiply the top equation by 19 and the bottom equation by 10.
And let's do -10.
-10 to make
Some
opposites. Yes, good call.
In the end, if you didn't, you would just then subtract the equations, but we're going to combine them. Okay.
Right.
So the top one, help me out with some math here.
All right. So we've got 19 times 40 is going to give us 760x. 19 times 10 would be 190. Y is equal to, and 180 times 19 is going to give us 3,420.
All right.
Okay.
And the bottom one?
That's going to be a little bit easier. So we're going to have a -220x minus 190y is equal to a -1,080. 18,000, sorry.
Yeah.
1,800.
Yeah.
Sorry, I was like missing something there. There we go.
Okay, now what's our goal?
Now we want to combine these two equations together. So we're going to add them, which notice that when we do that, the y's totally cancel out. Because
Okay.
I have,
These will cancel out.
right,
So let's add 760 plus, basically minus 220.
right. And that's going to give us our 540x. And then our 3,420 minus 1,800 is going to give us 1,620.
And then divide that by 540.
And that's going to give us 3.
Okay, so here's the deal. It said find each angle measure. It didn't really say find x or find y, but we need that to find the angles. Now, could we find some of the angles now that I have x
Yeah,
to 3?
absolutely. Because I know, like, for example, angle C was 40 times 3. So that's going to be 120 degrees.
So there's one.
And then when I take a look at angle D, that was 22 times 3, which is going to give us 66.
Okay.
Well, really, I can just use this. I could substitute my answers back into the equation, my x back into the equation to solve for y. But I know that those opposite angles are supplementary.
So if this is 120 degrees.
I don't even really need to find what y is as long as I can find the angle measure.
So if this is 120, so what's angle A going to be then?
That should be 60.
Because you're just doing 180 minus the 120
Right.
to get you 60. And then to find angle B, you're going to do 180 minus, what,
The
66?
which would be 114.
Now,
And there's all of our angles.
here's the issue, only issue with this is what if you made a mistake with X? Then you will have no way of checking to see if you did it right. So you could find, once you find X to be 3, you could put it back into one of the original equations.
Right.
Like let's say you put it back in here. So it would be 40 times 3 plus 10y equals 180. And then, okay, well that's 120. If I subtract that off, that's 10y equals 60. So y equals 6. So if I put 6 in for this here, 10 times 6
Is 60.
60. And then
So that's a
19
good
times
check.
6 is 114. So then we know, okay, these add up to 180, these add up to 180.
Right.
Okay, so the different options. All All right, and again, if you use substitution method, you have to get one of the variables by itself.
And just as a quick refresher on that one,
Okay.
so like for example, like on that top equation, I could have gotten that y by itself pretty easily. So I could have just subtracted my 40x and then divided by 10.
And what you end up with is y equals a negative 40x.
Negative 4x.
4x, sorry, I put plus your 18.
And then I would take that stuff that y equals and put it into the 22x plus 19y. That's what I would put in place of that y. And then solve to find the remaining variable. So just as a reminder in case you've forgotten how to do
The
that.
downfall to substitution method is not always is one variable is easier. Okay, neither one of them might be easy. You
may
might
get weird fractions
and I already know how you guys don't love fractions. So elimination method allows you not to have to do that ever.
Right.
So just something to keep in mind.